how long that thing is. Now, why would you ever need an arc length, right? I mean, it's kind of strange, but see, in Cal 3, what we do is we extend this out. Like right now, this is a curve on a flat sheet of paper, right? But imagine that you can take this concept and extend it out into three-dimensional space. So like that little gnat that was flying around, or mosquito, or whatever that thing was that was bothering me a little while ago, like it's flying around the room and it's tracing out a path in the room, isn't it? And if we were to keep track of where it is and watch it go through and then, you know, it lands, we could take that path and imagine straightening it out, and we could figure out its linear distance that it traveled through that path. Or you could, you know, it could be a rocket, or it could be an airplane, it could be a...
Make a function out of
they're called vector functions, curve functions.
slides or flying around randomly?
Well, no, you would have to somehow gather that data, but, you know, anything that's flying through the air, there's going to be some function that would match its flight, so to speak. And once you have that function, then you can do a lot of stuff with it. All right? So this is just the two-dimensional case. Later on, you go to three-dimensional. Let's do something a little harder. This next problem always seems to find its way onto my test. I'm not quite sure why. It just always, I just enjoy the next type of problem. Okay, x to the fourth over 16 plus 1 over 2x squared. Let me double check that. Yes. Remember, I said these have to be picked very special in order for them to work. Now that's a pretty nasty looking function, right? But it's going to work out beautifully in the end. So I'm just going to first remind you of what this function is, written a little differently. Isn't that the same? Okay. I did that because it's going to be a little bit easier for me to take the derivative if I rewrite it that way. So what is the derivative of, why am I taking the derivative? Because the formula needs the derivative, right? Squared. So I'm taking derivative. What is the derivative of this? 4/16, which is the same as 1/4, right? X to the third. Then? Minus x to the -3. So power comes out, subtract 1 from the power. That's where we are. I need to square this, don't I? Before I square it, let's all agree with this. That's this, right? I'm going to drop that negative exponent and drop it down. That's what the derivative is. And let's square. Well, that would be just this times itself, right? That's what that means to square it. And now you can expand it or FOIL it if you like that instead. What's my first multiplication give me? 1/16 x to the 6th. Next multiplication, be careful here. Close? 1/4 is right. Negative 1/4. Minus 1. What happened to the x cubes? They canceled, right? And a negative times a positive, that's going to give you negative. So we get negative 1/4 on that multiplication. What do we get on the inner multiplication here? Minus 1/4 again. Y'all see the x cubes canceling? Yes? How about my last multiplication here? Plus 1 over x to the 6th. which I could clean this up a little and say 1/16 x to the 6th minus a half plus 1 over x to the 6th. I just put the 2/4 together. All right, so that's my derivative squared. Yeah? I think I'm ready to go to the formula. I think I am, I'm not sure. That was all just my work to get me to this point. The length of this curve should be the integral from 1 to 2. Why is it 1 to 2? That's what I told you, right? I told you it was from 1 to 2. Square root 1 plus that. 1/16 x to the 6th minus a half plus 1 over x to the 6th dx. Can you clean that up at all? Or do anything with that? You can combine some like terms, can't you? That 1 that you have minus the half. Right? 1 minus a half is a half. Now, normally, if you saw something like that, you should get a little bit ill. Like you should feel a little sick if you see something like that, because that's not an easy integral. If the square root wasn't there, would it be easy? Yes, but the square root is there, so that is definitely no go. The only thing we've had with square roots that have saved us is like the previous problem we did basic U sub. No, right? No basic U sub here. Trigonometric substitution, but for that we needed something like a squared minus x squared, or we needed x squared minus a squared, or we needed like x squared plus a squared, right? That's what we needed. We don't have that, do we? So, any ideas? Split into 3 different roots. Can you do that? Is that a legal algebraic move? Why can't you split up roots like that? Yeah, like if I had this, why can I not do this? Because it's locked in? Well, if you ever forget that you can't do that, just think about it for a second. This right here is 13s, right? So this is root 13. If you think that this is true, then this should be 2 plus 3, which is 5, right? So is the square root of 13 5? No, then I must have messed up. Do you see what I'm saying? You can always go back and check yourself. So splitting into 3, no go.
Integration by parts.
Ooh, okay. Integration by parts. What are you going to choose as your u and your dv?
I would choose u as the left equation, the square root of and all that under, and then for dv dx.
Okay, so you want to make that your u and this your dv, and then when you differentiate that, enjoy. That's going to be nasty, right?
Yeah.
And then when you integrate that, you'll get an x. So I don't know, maybe, but I don't see it getting easier. I see it getting more complicated that way. But you're taking a swing. I mean, that's what you have to do here. You have to take swings at this. I'll give you a hint. There's no technique of integration that you need. You actually need to do some algebra right now. Okay, completing the square, that's what my other class wanted to do also. Try and complete the square. The only issue that I see with completing the square is that normally that works great with like quadratics. And this isn't really a quadratic. So maybe, can we hold off? Maybe we can find something else before?
That's factor.
How do you mean factor?
You do, I haven't totally worked this out, but I think like you can do 1/4 x to the third plus x to the negative third.
Wait, 1/4, what? Say again? 1/4?
X to the third plus x to the negative third. Is that
That's going to work. I'm not quite sure Everyone's going to see that. Okay, that is correct, but you can see it. We got to get to that. So that's very good. Give me anything that you, like, anytime you've seen a bunch of fractions together, anything that you could do to, like, make your life a little better sometimes. Combine them together? Common denominator? Let's just see what happens if we get a common denominator here. So do you all understand that we're kind of hung up on this part right here? That's pretty nasty looking. So I'm going to come over here, a little bit of scratch work. I'm just going to mess with that part in the blue. 1/2 plus 1/16 x squared, or x to the 6th, sorry. And then plus 1 over x to the 6th. Find me a common denominator. What would a common denominator be here? 16 x to the 6th. 6th, right? 16x to the 6th. So what would I need to multiply on the top and bottom of this fraction to get that? 8x to the 6th here, 8x to the 6th here. That would give me the common denominator of 16x to the 6th. How about this next one? And be careful, because this x to the 6th is actually up top, isn't it? So what would I need down there? Top and bottom. X to the 6th on the bottom and the top. Do y'all see what I'm doing? How about the last one? What? 16, 16. Okay? Y'all see what I did? All right. Now, put these together. What's the new numerator right there? 8x to the 6th. What's the new numerator here? X to the 12th. What's the new numerator here? 16. All over the common denominator. Okay. Now, here, let me arrange this in descending order on top. So now I don't have any fractions. And I'm hoping that at this point, it's a little more obvious that the numerator is something very special. It's two things multiplied together. You can factor the top. What does the top factor to be? X to the 6th plus 4, and then x to the 6th plus 4 again. Do you see that? This times this will give you x to the 12th. This times this, 4x to the 6th. This times this, 4x to the 6th again. That gives you 8 of them. 4 times 4 is 16. Agree with that? And then this is x to the 6th plus 4 squared over 16x to the 6th. Laura, I know that's not what you did, but it's the same. It's going to give us the same thing at the end. Yes.
You said this problem is on the test usually. All this.
This is always, yes. I mean, I almost without fail put this on the test because this is algebra that you all need to know how to do. Be expecting it. That's the thing. You should expect to have to do this sort of algebra on the test. All right? Good? Now, why am I excited about that being in there instead of that? What am I happy about? This is going to go right here, right? Yeah, when I take the square root of this, if I take the square root of the top, the square is going to go away, right? And the square root of the bottom is pretty straightforward. Yeah? So let me continue. So I have equals integral 1 to 2 square root of this thing, x to the 6th plus 4, and then 2, and then 16 x to the 6th dx. Now go ahead and take the root on the top and bottom. The root of the top is just x to the 6th plus 4. The root of the bottom is 4x what? I've heard fourth and third. Third. When you square x cubed, you get x to the 6th. right? Power to a power, you multiply the powers. Questions? I'm happy, there's no more root, right? It's good. How would you integrate that? You could split that into two integrals, couldn't you? You could go integral 1 to 2, two things here. You can go this over this over this, right? So what's x to the 6th over 4x cubed? X to the 3rd, right? With a 1/4 out in front of it. And then what's the last one? 4 over 4x to the 3rd. It's just plus x to the negative 3. So Laura, you saw that from this to here. That's really good. All right. You could integrate that, right? I mean, term by term, antiderivative of that, antiderivative of that. Power rule, pretty clean. Yeah. Equals dot, dot, dot. So I'm going to stop there. All right. You all happy? All right, got about 22, 23 more minutes. Next problem, I hope you'll enjoy. Do you remember that problem I did a while back when we were doing areas? Didn't I prove to you that the area of a circle was pi r squared? Do you remember me doing that? Y'all were all excited, or like throwing confetti at me at the end. Do you remember that? That's the way I remember it. Okay, so here's what I'm going to do. I'm going to go back to the good old circle. And I'm going to throw a formula up here that we've all seen. Circumference. The circumference of a circle is 2 pi r. Why? Because that's what you've been told, right? Now I'm going to show you where it comes from. So what we'll do in order to do this is we're going to imagine that we orient this circle at the origin like this. And then, do you remember we had to come up with the equation of a circle? And the equation of this was x squared plus y squared equals r squared. And we went as far as even solving that for y. And we said that y would be equal to square root r squared minus x squared. In fact, it's actually plus or minus. The positive root of this would draw the top half of the circle. The negative root would draw the bottom half. Does this ring a bell? Yeah? You all can respond. It is okay. Do you recall it or not? Yes. Yes? Okay, thank you. So, what I'm going to do, see if I can convince you of this. I'm just going to look at this first little quarter of the circle right there. I know that I can draw that piece of the circle using the function f of x is equal to this. And I can do that on this interval, bless you, 0 to, what is that? 0 to what?